Boom. All right, Julian, welcome back. And today we are going to be discussing current electricity. That is chapter 7, physics 124. And current electricity is quite a very simple topic. It's broadly divided into the concept of drifting velocity and simple electric circuits. From simple electric circuits, we're going to be talking about shunts and resistors. Okay, shunts and multipliers, I wanted to say. So it's quite a very simple area, and I think it's going to be a very interesting topic. So let's start. Current. What is current? Current is a rate at which quantity of charge flows on a conducting material. And that simply means that current is quantity of charge per unit time, right? That's Q over T, which is coulomb per second, aka ampere, right? Now, if N quantity of charge flows through a conducting material for T amount of time, then the current becomes NQ divided by T, right? It is important for you to know that current is a scalar quantity, not a vector quantity, because some may argue that current has direction. Come on, the electron moves in the opposite direction to current, so it should have magnitude and direction. No, current does not follow vectorial sum or vectorial resolution of parameters. That's to say, if you want to add current, you can't add it in x and y direction. It makes no sense. But current density can do that. All right, but we're coming to that anyway. So the next thing we're going to talk about is the concept of drifting velocity. Drifting velocity. Now, before we know what drifting velocity is, it is important to know what happens to a naked wire when no current flows through it, or when no electric field is introduced into it. Once you introduce electric field, you automatically introduce current, okay? Good. Now, if I have a wire that current does not flow into it, electrons are already inside that wire. So those electrons are actually in constant random motion, moving and colliding with each other and probably with the walls of the wire. So because they move in a random motion, they have zero average energy, or they have zero average velocity. In other words, their average velocity at that point in time is equal to zero. Why? Simply because they move randomly, colliding with each other without a specific direction. And because they move randomly, they possess kinetic energy called Fermi kinetic energy as a result of the Fermi velocity with which they move. So the velocity at which they move when no current is passed through it is called Fermi velocity. And because they are in motion, they possess Fermi kinetic energy. And Fermi kinetic energy is a half mv squared. The F there is is Fermi. So V Fermi is what we are saying now. So V Fermi velocity. So you can make that the subject of the formula. You have the root of 2E, that's kinetic energy now, all over the mass of the probably wire, as the case may be. Okay, good. And take note, because they possess kinetic energy, and remember, temperature is the average kinetic energy of the gas molecule. So temperature generated in that wire is called the Fermi temperature. The Fermi temperature now becomes the ratio of the kinetic energy to the Boltzmann constant. And Boltzmann constant is 1.38 times 10 raised to the power minus 23. Minus 23, yeah, minus 23 like in Avogadro. But what is the unit? Minus 23 meters per second all squared per Kelvin. Yes, you find that you can derive that unit from kinetic energy, which is a half mv squared. V there is m over c. So it's actually kilogram meters per second all square per Kelvin, right? Good. So that is temperature. So what we are saying in essence is that all these things are happening when there is no current flowing through the metallic conductor. They are randomly moving. Now, when an electric field is introduced, or simply put, current is passed through the wire, all these electrons that were initially moving randomly with each other will face one direction, and they will move in a unified direction. And as they are moving, they now possess average velocity. Now that they possess average velocity, what happens? They move at a velocity called drifting velocity. The velocity with which they gather to move is called drifting velocity. And that velocity is in the opposite direction to the electric field introduced. So if the electric field is coming due east, they are moving due east. In other words, they are moving from south to east. You get it? So they are coming in opposition to the introduced electric field. And that is why they would tell you that current is going this way, electrons are going in the opposite direction. You get it? So the velocity with which they now move is referred to as drifting velocity. And that velocity is given by I all over N. I is current, E is quantity of charge or electron as the case may be. Then N there stands for the density, okay? While A stands for the cross-sectional area of the wire, which is pi r squared. So N is the density, which is Avogadro's number divided by the volume. Density is mass over volume. So Avogadro's number is 6.02 times 10 raised to the power 23 all over the volume. And then as for I is the quantity of charge all over the time. Then as for density, take note at times density can also be come into play where you have mass over volume. So you can always play your job. If you're looking for volume, for example, because there are some cases where you will need to look for volume. Volume is given to you and you have to generate the mass through Avogadro's number, and then you apply the density. Just remember that density is mass over volume, okay? So you can always randomize your job there. Also, current density. Current density is key. Current density is the current per unit area. Current density is a vector quantity. Why is current density a vector quantity? This is because it decreases, this is because it describes how charges flow at a given point. That is, the magnitude and the direction of charge at a given point. But current, however, is a scalar quantity because at all points in a wire, current is equal. But as for current density, it describes the magnitude of current at a particular position. So it is a vector quantity. Just take it like that. Okay? So now, drifting velocity can also be expressed in the form of current density. How? Because current density is simply I over A. And if you remember, drifting velocity is I all over N, which is ENA. So I all over A can become I, which is current density, and your drifting velocity becomes I divided by NE, right? Very, very important. Now that takes us to the concept of simple circuits. A simple circuit is simply a circuit that comprises a battery, a resistor, a capacitor, or any of those three simple components in variable manners. That is a simple circuit. A simple circuit, a cell, very important, EMF of a cell. When you talk about the EMF of a cell, you're talking about the power. The EMF of a cell, it pumps electrons round the wire. All the electrons in the wire are being energized by the EMF of a cell. So that is the job of EMF. So every cell has an internal resistance represented by small letter r. In an open circuit, the potential difference across the terminals is equal to the EMF of the cell. But once the circuit is closed, the potential difference across the terminal cannot be equal to the the EMF of the cell. Why? Because of the presence of the internal resistance. The internal resistance will decrease the potential difference by a given multiple factor of itself and the current. So if, for example, a battery is 12 volt and has an internal resistance of 0.2, and a current of 2 ampere is flowing in that closed circuit, what will happen is that the potential difference at the terminal will drop by 2 ampere times 0.02, which is about 0.4, and you now have 11.6 volt at the end of the day instead of 12 volt. That shortage is as a result of the internal resistance of the cell. And therefore, the potential difference across the terminal in a closed circuit is V equals to E, which is the EMF of the cell, minus the opposed voltage, which is I small r. So that V there is I capital R, then you now have EMF minus I small r, and then from there you can make I the subject of the formula, and you get the formula for electric current in a circuit to be the EMF of the cell divided by the algebraic sum of the external resistor and the internal resistor. Now take note, external resistors are always greater than internal resistors. Very important. Facts. Number one, when you have 3 cells arranged in series, the effective EMF is simply the algebraic sum. But by the time the direction of the cells are swapped, you apply negative when necessary. As for the internal resistance, it's also the algebraic sum in series. Now, what happens when you now have 2 or more cells arranged in parallel? The effective EMF is equal in all the 3 cells. That's the gospel truth. If they are not equal in all three cells, then you will need Kirchhoff principles to solve that kind of problem. What about the internal resistance? The internal resistance becomes a reciprocal sum of them all. Now take note, whenever you swap the position of a battery when it is arranged in series, internal resistance doesn't swap itself. Opposition is opposition, irrespective of the direction of the cell. So R will still remain algebraic sum in series, even though the cells position are swapped against the others. Very, very important. Now that takes us to Ohm's law. According to George Simon Ohms, the magnitude of current flowing through a metallic conductor is directly proportional to the potential difference across the terminals, provided that temperature is kept constant. Is directly proportional to what? Potential difference. And of course, from there, you will, but inversely proportional to resistance. So you will now see current direct to voltage, but inverse to resistance. Then you have V is equal to IR. From there, you can generate multiple relationships between current and voltage, I1, V2, stuff like that. So the current is direct to voltage, and the same current is inverse to resistors, okay? So you can always do that. Take note, this law is only applicable to ohmic conductors. It is not applicable to non-ohmic materials. Ohmic conductors are good conductors. Non-ohmic materials are semiconductors like diode, triodes, transistors, and all that. So this law does not cut across them because it is not applicable in them. Right. Now that takes us to the concept of resistors. Resistance of a conductor is simply the opposition to the flow of electrons or electricity through that conductor. A resistor or a material is said to have a resistance of 1 ohm if only it permits 1 ampere of current to flow through it when 1 volt is applied across the terminals. That is the meaning of it to be 1 ohm. It will only permit 1 ampere of current to flow when 1 voltage is applied. You get it? So you can do the mathematics and play with it. Now, the resistance of a material depends on the length of the wire, which is which is directly proportional to the cross-sectional area of the wire, which is inversely proportional to it. And then 3, the nature of the material, metallic conductor, non-metallic conductor, semiconductor. Resistance is dependent on that. And then it is also dependent on temperature. Oh yes. Resistivity and temperature are not mates, bro. When temperature increases in a metallic conductor, conductivity decreases, but resistivity increases. That means resistivity and temperature are directly proportional. Now take note, in a semiconductor, increase in temperature also increases conductivity. That is the gospel truth. But when we talk about impurities, when you add impurity to a semiconductor, impurity will actually increase the conductivity of the semiconductor. But it doesn't happen in a conducting material, a pure conductor. If you add impurities in a pure conductor, it will decrease the conductivity of that material. Very, very important. And that simply means that impurity is directly proportional to resistance in a pure conducting material. But in a semiconductor, the reverse is the case. And it's important for you to know that resistance is directly proportional to the length of a wire, but inversely proportional to the cross-sectional area of that wire. And when you find a constant of proportionality, which is resistivity, it will give you rho to be equal to RA over L. And rho is measured in ohms per meter, right? Very, very important. From there, you can have relationships as R1, A1 all over L1 equals to R2, A2 all over L2 as the case may be. Resistivity is directly proportional to even the smallest impurity and also varies directly to temperature, which we have discussed ab initio. So you will see a relationship as rho equals rho naught, all in bracket 1 plus alpha bracket T minus T naught. And T naught there is always temperature in degrees Celsius, usually 20 degrees Celsius, okay? So rho is the final resistivity, rho naught is the initial resistivity, and then that alpha represents the temperature coefficient of resistivity of the material, usually measured in per degree Celsius, right? That takes us to conductance. Conductance is the measure of the induced force it offers to the flow of electrons in a particular conducting material. Conductance is directly proportional to cross-sectional area, but inversely proportional to the length of the wire. Conductance is moreover inversely proportional to resistance. And the constant of proportionality here is referred to as conductivity, represented by sigma. And that sigma is measured in CMS. Conductance is measured in CMS per meter, while conductivity is measured in CMS. Take note, conductance to conductivity, resistance to resistivity, right? Very, very important. Conductance is inversely proportional to resistance, while resistivity is inversely proportional to conductivity. So you can have a relationship between conductivity and resistivity, and you can also have a relationship between conductance and resistance. Take note. That takes us to resistors in series and in parallel. When resistors are arranged in series with voltage R, V1, V2, V3, the effective resistance there is the algebraic sum. Voltage is not algebraic sum. Sorry, voltage is algebraic sum because current is constant when it is in series, right? Good. Now, when you now arrange them in parallel, it is important for you to know that the effective resistance is the reciprocal sum, while the current becomes the algebraic sum because current will split into three different places, right? Then while voltage in a parallel arrangement remains constant. And this is the same thing we did in the previous chapter. If you remember, UIQ, same. You get it? Good. While VC varies. All right. So the next thing we're going to talk about is electrical energy. We already know that electrical energy is the work done, or let's put it this way. Electrical energy is given by, or let me say, the electrical energy given by a charge passing through a device. Oh, the electrical energy, this is just crazy. I don't even understand what I wrote here. But all you need to know is that work done, which is energy, is equal to the quantity of charge times the potential difference, okay? So energy is QV. And because energy is QV, and you know that Q is equal to IT, energy, which is work done, becomes ITV, right? Good. Now, electrical power dissipated. This is the work done, the rate at which work is done. And work done, you already know as ITV. So, divided by the time, you get IV. So, power is IV. And when you substitute V to be IR using Ohm's law, you will have power to be I square R. And when you substitute I to be equals to V over R, you have power to be V square over R. So power in all is IV equals to I square R equals to V square over R. And power is measured in joules per second. Also take note that the heat energy dissipated in a conductor of resistance R is given by the product of the power and the time taken. Yes, energy is power times time. So power you know as IV multiplied by the time, that's ITV. R square R multiplied by the time R square, I square RT. And then V square over RT as the case may be. Also take note, it is also called Joule's law of heating or I square R loss. Yeah, this heat process we are talking about. And also remember that 1 kilowatt per hour is equivalent to 3.6 times 10 raised to the power of 6 joules. Kilo stands for 1,000. 1 hour is made up of 3,600 seconds. So 1 kilowatt hour is equivalent to 3.6 times 10 raised to the power of 6 joules worth of energy. Right? Now the potential difference V across a capacitor in an RC circuit is given by V equals to epsilon in bracket 1 minus E raised to the power of minus T over RC. Yeah, that is in an RC circuit. This voltage across the capacitor, which is the RC circuit, decreases by V equals to V naught E raised to the power of minus T over RC. And of course, V naught, as you already know, is Q all over C, right? From Q is equals to CV, if you remember pretty well. So, and that is that for that. So that takes us to the concept of shunts and multipliers. A galvanometer is an instrument meant to measure very little amount of current. It's an ammeter used to measure very little amount of current, which is in milliseconds or in milliammeter, I wanted to say. Now, but if you want a galvanometer to measure a very high current greater than the capacity it usually measures, then you will have to bring in a resistor called the resistor or the shunt resistor. And that shunt resistor you're bringing in will be connected in parallel to the galvanometer. The reason why you have to connect it in parallel to the galvanometer is because as current is coming, current is going to split. Now the resistance of the shunt will have a very high resistance. So it will capture majority of the current coming so that a little amount of current, reasonably big enough, can flow through the galvanometer while the galvanometer picks it. However, you are also advised to introduce a resistor before you get to the galvanometer in series. And that will protect the galvanometer from blowing in case the current coming there is still very high. So for you to now calculate the value of this shunt resistor, all you need to do, because they are in a in a parallel arrangement, the voltage of the resistor, which is the shunt resistor now, is equal to the voltage of the galvanometer. So Vs is equals to Vg, and Vs is ISRS equals to IGRG. Ig is the current going through the galvanometer, and Rg is the resistor of the galvanometer, right? It can be internal resistor or something. But then from there, you can make your resistor of the shunt the subject of the formula. And also take note that the current of the shunt is the difference between the incoming current and the current going through the galvanometer, right? Good. So now, what if you want to use a galvanometer to detect high voltage? A galvanometer is not designed to detect voltage, but however, there are some settings you can undergo and make your galvanometer detect voltage. And for you to be able to achieve that, you will need another type of resistor called a multiplier. And this time around, that resistor will have to be connected in series with the galvanometer, not in parallel. Yeah, in series with the galvanometer. Now the big question is, why do you have to connect it in series? Because you want it to measure voltage. And remember, the voltage flowing in a series arrangement are not equal. And because they are not equal, then the resistor of the multiplier will take majority of the voltage so that a little amount of voltage will go through the galvanometer. You get it? So the first thing you have is a resistor of the multiplier, with current flowing through it, and then the little amount of voltage that will be left will now go through the galvanometer with its internal resistor as well, and then from there you now apply the law of series arrangement. Remember, voltage V is equal to the algebraic sum of the two terminals. That is the voltage of the galvanometer and that of the shunt, because we have voltage across each of them. So by the time you do that, you will have V is equals to VG plus VM. And VG is IG R small rg. That's the current of the galvanometer and resistor to the galvanometer. Now, plus the current of the multiplier and the resistor of the multiplier. Now, take note, because they happen to be in series, the same current flows through the multiplier and the galvanometer. So, on that note, Ig plus Ig becomes equal to Im equals to the initial current. So, you make current the subject of the formula. Your resistance of the multiplier becomes V all over I minus R. Good. And that is the end of this amazing chapter. We are done with current electricity. In the next chapter, we are going to look at Kirchhoff's principle and complex circuits. Boom. See you when we meet again, Julie Ben. Have a great day.